Hi, I'm Carl, and in this video we're going to go over questions 57 to 60 of section 3 of the pink booklet. So this is a question about someone jumping, and I've got a diagram that defines J and C here. And we've been given a couple of equations. So I just want to point out first that this is force equals kmg. Don't forget mg is really just weight. So k is just a multiple of the weight. And then we've got some equations for J here, which we'll come back to in a minute. So question 57 says, consider jumps on Earth and the Moon. A person will only leave the ground for what values of k. So I think just to simplify this, let's think of the person just as this dot, and this dot will have a weight of mg. And acting upwards, we've got this jumping force, which is going to be equal to kmg. In order for there to be a resultant upwards force, then k would have to be greater than 1. Now, it does say about how k would be different on the Earth or on the Moon, but that really just calls into question what g is. And we're told that g is the acceleration due to local gravity, not just Earth's gravity, but local gravity. So on the Moon, it's going to be a sixth of what it is on Earth. So that means that k has to be greater than 1 in both senses. That means that the answer for this one is going to be B. 58 says, suppose a person jumps 11 times as high on the Moon as on Earth when using equal force. How large is the force exerted? Okay, so this one's a little bit more involved, but really we can just think of a ratio between the two. So we know that J Moon divided by J Earth is going to be 11. And we get this from the question because the person's jumping 11 times higher on the Moon. So if this is the case, let's think about what J Moon actually is. So we're told, and we're given this equation, that it's c upon 6 ke minus 1. And we also know that J Earth is going to be c upon k Earth minus 1. So if we're going to take a ratio of them, we can just do it like this. And we can cancel these c's, and then we know this is going to be equal to 11. So we get an expression then that looks like this. We've got 11 equals 6 ke minus 1 over ke minus 1. So if we multiply both sides by ke minus 1, we get 11 upon ke minus 1 equals 6 ke minus 1. So then multiplying that out, we will end up with 5 ke equals 10. So ke obviously then equals 2. So what does that mean? So we know that the force on Earth is going to be the k on Earth multiplied by the mass times the gravity. And gravity will be local, so it'll be on Earth as well. If the force exerted on Earth is going to be 2 times the person's weight, it's going to be their weight on Earth, remember? And that's really our answer. We know that the force exerted is going to be 2 times the weight of the person on Earth. And that gives us an answer for 58 of C. 59 says, consider a person who jumps on the Moon using a force that is 6 times their weight on the Moon. If a person uses equal force on Earth, they will what? Okay, so this one is sort of worded in a little bit of a complicated way, I think. But let's again just simplify it to this point. So this is the person, and on the Moon, let's say GE equals 10 and G on the Moon equals 10 over 6. So their weight acting down is going to be mg. And on the Moon, that'll be mg Moon. And acting up, of course, they have this force, which is 6 times their weight on the Moon. And this is obviously for the Moon. So if we do the same thing then on Earth, we have our dot here. We're acting down with a weight of mg Earth and acting up with the same force, which is 6 mg Moon. If we resolve these forces, then we know this is going to be 6 times the mass times 10 over 6, which equals 10m. And this is also going to be 10m, which means that the force acting up and the force acting down are equal. So there's no resultant force, so the person will not leave the ground. So question 59, the answer is A. And then finally, we've got question 60. And this one's a little bit tougher. It says, consider a planet with 1/3 the gravity of the Earth for jumps using equal force on the other planet and on Earth. Which of the following is correct? So some of you might be able to just look at this and know the answer straight away, if it seems sort of intuitive how these equations might work. But for me, I think it's easiest just to try and go about it in sort of the simplest way, even if it's a bit longer, for the sake of explanation. So what we're going to do is we're just going to form a table here, and we're going to put in planet, Earth, and Moon. And we've got a couple of different values. So we've got K, we've got our mass, and we've got gravity. So if we say on Earth, the gravity is going to be 10, on the planet is going to be 10 over 3. And as we said, on the Moon, it's going to be 10 over 6. Mass doesn't change, so we can just call that 1. And K we'll come back to in a minute. So we know that for the jumps are all using equal force on the other, equal force, right? So that means whenever you multiply these together, you get the same value. It doesn't matter if it's going to be on the planet, on the Earth, or on the Moon. So let's say that on Earth, we've got a K of 10. Just for the sake of argument, we'll say the K is 10. On the Moon, then it would be 60. And then on the planet, it would be 30. And this is how they would all equal 100 if you multiplied them out. So the point I'm trying to make here is that as the gravity changes, the K changes, but it's inversely proportional, if that makes sense. So then what does this mean for the different values? So J planet is going to be C upon K planet minus 1. So we could say that's C upon 29. J Earth then is going to be 9C, and J Moon is going to be 59C. So the C's don't actually matter because we're going to be dealing with ratios here. So let's have a look at J Moon over J Planet and compare that just to J Moon over J Earth. So J Moon over J Planet is going to be 59 over 29. It's a bit of a dodgy fraction, but we'll move on. JM, we know is going to be 59, and that's going to be over J Earth, which is 9. So what does that tell us? Well, we've got a couple of different options. We could say that this ratio is going to be equal to, is going to be greater than, or less than, or a third of the other one, or equal to 2. So we know that J Moon over J Planet, that's not going to be equal to 2. That's this one here. J Moon over J Planet, which is this one here, is not going to be equal to 2. If you looked at it here, you can see 60 and 30. But don't forget, you've got this minus 1 that makes it not as simple when we're working it out. So we can rule out D straight away. When comparing these two fractions, we can see that one is not going to be a third of the other. So we can rule out C. And then we've got just two options, which side is bigger. And obviously we can see that that side is going to be bigger. The right-hand side is bigger. So that gives us this expression here. Jm over Jp is going to be less than Jm over Je, and that gives us an answer of B for question 60. So a bit of a tough question, but that was questions 57 to 60 of section 3 of